full disclosure, these are just warmed over slides from a talk I gave 4 months ago.
I
But
was going to say 75.
75?
This is one of 75.
Oh yeah. Well, most of those are, or a third of those are slide transitions. Only 44 slides actually. But anyway, okay, cool. So yeah, so I'm going to be talking about work I did. This is specifically one paper, but also some smattering from other stuff for understanding this specific gravitational wave event 191109 and how glitch mitigation affects it. Okay, so first off, I'm going to spend an hour telling you about a single black hole. Can I get this?
Control L.
No. There we go. Okay. Okay. Why am I telling you about a single gravitational wave event? The answer is, well, so one of the main things we want to understand with gravitational wave observations is where the sources we observing where they're coming from. Generally speaking, when you talk about black holes, a black hole binary that merges, their formation channels can be divided into one of two categories. Either they were born as stars that evolved in a binary and then each went supernova, each formed a black hole and then merged, or they did not do that. Okay? So there's lots of subways within, or subcategories of formation channel, but generically speaking, it is one of those two, obviously. And they do produce different properties in their system. So part of what we're looking for with gravitational waves, we're trying to find the signatures of those different formation channels so that we can understand, how the universe works and where these black holes are coming from. Okay, so black hole mergers, very simple, actually, right? One of the simplest physics problems you can do because there's only 15 parameters, and that's literally the actual number of parameters, not fudging it, that's it. So we have two masses, we have 6 spin parameters that take the form of 2 vectors, and then we have 7 parameters that are less important for astrophysical purposes about where and when this happened. Okay, so we have lots of different ways of modeling this. Waveform approximates, and they take some set of parameters and they produce a prediction of what the waveform looks like. There are lots of these, some of them are better, some are worse, but we can use any of them to just infer the properties of what we saw by Bayes' theorem, okay? We assess how likely it is to have gotten the data we saw under the assumption of some parameters and some forward model. We do this many times under some set of priors, and we construct posterior assumptions about what the source actually looks like. Okay, and so what this looks like is something like this. Well, so this is GW191109. And according to the 2 waveform approximates, which the LBK used in analyzing it, it's pretty interesting. So you can see, so the source mass is of the primary, so this is the larger of the 2 black holes, is sort of peaked in like 60, 65 region, which is quite heavy by our standards, and the secondary is not light either. More exceptional is this chi-effective parameter. I forgot how I made these slides. Okay, yeah, so high component masses. Why does that matter? So when we look at the 2 formation channels, broadly speaking, right, we have, as I said, isolated or dynamical. So the isolated systems are limited in the masses that they can form by the physics of the supernova. So we know about this process called the PISN, parent stability supernova, which we expect to set essentially a upper limit on the masses that can be, or the mass of a black hole that can be formed by a supernova. There's other even heavier black holes, but those are out of scope for this discussion. So basically, we expect at some point that the population of supernova-generated black holes will turn off because of this process. We don't know exactly where that point is. There's a lot of uncertainty in that for the modeling. We know it's around 50 or 60, like in that range. So if you see something that's heavier than that, especially if you see something significantly heavier than that, you start to say, this doesn't seem like it could have been formed by a supernova. By contrast, dynamical formation could be hierarchical. That is, you take 2 black holes, you smash them together, and then they go flying off. But if you're in some dense enough environment, like a globular cluster or maybe an AGN, then there's enough stuff in the way that they will incidentally interact again and form another system and have another merger. So obviously, in this case, you have the mass of two black holes has made one black hole. This black hole is now heavier. So this is a way to potentially get around the PISM gap and form these heavier black holes. Okay. The next thing about 191109 is the spins. So the spin, this chi-effective parameter is a little hard to describe. It's basically the amount of the spin that is counter to the orbital angular momentum. So it's moving like this, but the spin vectors are going like this. So it also has potentially, depending on the approximate, some indications of precession. Precession in gravitational waves means the spins are in the plane, and they're going like this, and then this causes the plane of the orbital plane to wobble. Okay, so precession is interesting as a physical process, but in either case, this tells us something about the spins, because isolated formation channels, for a variety of reasons, not my department, won't try to explain, prefer pretty small spins probably, and also prefer those spins to be aligned with the orbital angular momentum and the binary that generated them. And so you're expecting like low spin measurements and probably all positive aligned spin, if any. Contrast, dynamical formation, I mean these two, you have two things that just sort of find each other randomly, so you expect the spins to be isotropically distributed. There's maybe AGNs or something would align them, but probably isotropic. And in the hierarchical formation channel, then you would also expect the spin magnitudes to be quite high, because in the first merger, you've got the orbital angular momentum all converted into the spin of the remnant, and so that means you have a lot of spin, 0.7 being around the numbers. So if you see something that is like high spins and not in the direction of the orbital angular momentum, this implies to you that it is likely hierarchical, likely dynamical. Okay. So given that, now I said something about waveform approximates. Let's introduce a better approximate. Yeah.
So the chi-effective combines the two spins together in some sense?
Yeah, it's a mass-weighted average of the z product, or the z component of each spin.
Is it possible to measure the individual spins?
Yes, it is. It's generally, these are worse measured, and chi-effective is generally a good proxy for the dynamical formation. I mean, it's a good proxy for the aligned spin component. There's potential interest in, like, if you see one that's strongly up and one strongly down, but this is quite hard to measure. So we not really have measurements like this yet. We may in the future. Yeah, good question. And I should say also, chi-effective is also less effective as a parameter for higher mass systems like this. It's very good for low mass systems with lots of cycles in the post-Newtonian regime. It's less effective here, where we're kind of not in that regime for a lot of it, but it's good enough. Okay, so I said we looked at the two approximates that the LBK used. Well, so for high mass systems, there is actually a third waveform approximate. So that's, again, a forward model, which is just better, and that's the NR surrogate. And so you can see, it's interesting that actually this waveform model takes all the things that were interesting about 191109 and like turns them up to 11. Like the mass is well localized to be a high value, and in particular the chi-effective is almost 100% certain to be negative. So various studies have been done that basically say, like, if you had a system that was like this strongly negative chi-effective, it's pretty much 100% chance that it's dynamically formed. There's assumptions in that. I won't try to get into it, but it's a very strong indication. Okay, and it's also, and this is worth noting, an outlier. The rest of the population does not look like this. This is all the heavy systems. So there are some exceptions in lighter systems that have negative spins, but all the heavy systems, you can see the spins sort of cluster around 0. There's a few that are pretty high, positive aligned spin. 191109 is way over here. And I highlight these other cases. There's a Nature paper about this one because it's a bit further up than the others. So like that's the situation we're dealing with. You can see 191109 is much more of an outlier than any of those. Okay. So why am I, so I'm giving glitch mitigation talks. There's a catch, and the catch is, well, let's look at the data. So this is the CBC track in the LIGO Livingston detector. You can see the CBC pretty clearly. Okay, this is obviously CBC power. Follows our reconstructed time frequency plot very well. then this is weird. So this is clearly on the CBC track and looks like CBC. This is just kind of a blob hanging out there. What's the deal? I will spend the next half hour telling you what's the deal. Okay. So we happen to know that in both detectors actually, there was high seismic activity going on, which causes the detectors to not operate in nominal form, I guess. So in particular, this is a kind of glitch called a scattering glitch. I'll go into a little more detail in a second. But basically, we know that these glitches can be caused when the ground is moving a lot and causes stuff in the LIGO detectors to move a lot. And we're able to predict roughly what that glitch should look like. We saw it happening in the seconds before, and this is, ground motion doesn't just stop, so if it's happening 4 seconds before, it's definitely still happening when the event occurs. And we can predict where in frequency it should happen, and you can see smack dab on our little blob here is the prediction of a glitch arch. So we have something in our detector that is making us say there should be a glitch in this place where we see something that looks anomalous, but it doesn't quite look like what we think this glitch should look like, and I'll get into what that means now. Okay, so now let's take a little digression in the world of glitches. So I'm going to be talking specifically about scattered light modeling, but scattered light is not the only kind of glitch. There's many. They have all sorts of funny shapes. Some of them are bad, some of them are real bad. Scattered light is not actually that bad, but it can be troublesome. So slow scattering takes on this form. So it looks like a bunch of arches sort of stacked on top of each other. This is actually, scattering comes from the mechanism. It is light scattering off of a surface, and this is multiple bounces off of the surface. You get a new arch, it gains. Basically, this is Doppler shifting of the laser as it gets bounced by the relative motion of the scattering surface, and so every time it bounces, it gets more relative motion, gets more Doppler shifted, and so it goes further up in frequency. Fast scattering is a related process that involves different environmental drivers. Okay. So the suspension system in LIGO is very good. It is an extremely impressive bit of technology where you have a 4-stage pendulum in order to insulate the detector from the motion of the ground, because any significant ground motion will make it impossible to detect anything. And so this is very good. It does a very good job, but it's not perfect. And in particular, it's worth highlighting also something about how it works is that it has, in order to control the detector, it's basically you need a cantilever. So you have the regular test mass, and you have a second test mass, exactly the same, that's not doing any of the science, but it is used to balance out this first one, and it also contains this stuff. So this gold stuff is an electrostatic actuator, and what it's used for is basically if we need to, keeping the detector in lock requires controlling where the test masses are, and so this applies, like it gains charge to electrostatically push on the test mass so that it's in the location we need it to be. Now, it's colored gold because it is made of gold. Gold, very shiny. So light likes to bounce off of gold, and this is a problem. So the other, it's a problem because as you can see, the light is going. So I mean, these are mirrors, but they aren't perfect mirrors. That's the point. So light is going through this and then coming back out, which means that if the Gaussian beam has any width, and it's a Gaussian beam, so it does, light will get onto the gold bits and it will reflect off of them. Now, so this matters when you have multiple bounces, as I said, and in particular it matters if this part, if the cantilever is moving with respect to the test mass. So if there's relative motion in these, then you'll get relative phase accumulation from the extra bounces. And that will end up looking like this. So you can take the motion, the ground motion, you can take its frequency and you can correlate it to the frequency of slow scattering. So we're very confident that this is what we're dealing with. And the good thing is, okay, well, so this is a 4-stage pendulum, but the bottom stage you can basically treat as isolated and as a single pendulum. And so we can model this by just saying that this thing is a harmonic oscillator, that it will have some motion, and then using classical physics we can predict Doppler shifting and phase accumulation and phase difference due to that, and produce a model for our glitch. Okay. And by taking a frequency, so this frequency of time model is what I use to produce those like arch traces, and now I can also produce a forward model, just like my CBC forward models, for the glitch behavior based on just a set of parameters without knowing anything about what is happening in the detector, just as a generic model. Okay, and this has a few parameters that I'll mention real quick. It's got the width of these arches is set by, this is the ground motion, the inverse of the ground motion. It has some time at which it's occurring, obviously. We choose some arbitrary place to basically put where the first arch that we're going to analyze is. And we also know that the distance between two arches is fixed. So it must be an exact, these are all multiples of each other, so they must have this fixed relationship. And then they each has an amplitude and a phase. Okay. And in Bayesian inference for gravitational waves, this is our normal likelihood. So we're basically just subtracting off the waveform that we're predicting from the data and then evaluating how likely the residual is to have occurred due to Gaussian noise. So now we can just augment this by also subtracting off the glitch model and see how likely that residual is to occur due to Gaussian noise. Okay. Cool, so that's the technical bits. So now let's talk again about 191109. So looking at this, as I said, we know what this should look like. We know indeed that this 24 hertz bit looks, it's hard to see, but if you look at this overall trend here, this is like, there is gray patterning underneath the green line that tracks with where it is. The 36 hertz thing does not look like a scattering arch. Scattering arches, as I said, should all share this width property. This one doesn't. That doesn't look like anything, but it is in the frequency domain where it should be. Now, if you know anything about glitch mitigation, you will stop me and say, Rhiannon, what about Hanford? Hanford did a glitch at the time, actually the same kind of glitch, but the glitch wasn't overlapping. So, in principle, we should be able to understand more about the astrophysical signal by the fact that it is coherent in both detectors, but the glitch is not coherent. Right? The glitch is a different glitch in each detector, and therefore, if you model power that fits in both detectors, this should allow you to discriminate against the glitch power. Unfortunately, though, at this time, and currently still, Hanford has much worse sensitivity at these low frequencies that we're going to be interested in than Livingston does. So this means that we're kind of flying blind in the low frequencies, and we're forced to rely on Livingston's interpretation, where we don't know if a little bit of power is going to be glitch or if it's going to be the CBC. So this makes our life hard. Okay, so the first thing we did is analyze the glitch, analyze the data and just make a reconstruction of it. We actually do this with two different parameter estimation pipelines, just to be sure. One that works in the frequency domain and one in the time domain. Okay, and so you can see here, this time period is where the 36 hertz power is. This corresponds here, so you can see sort of the data going up and down here, and the models are both capturing it. So this data is what corresponds to this power, and this data is being modeled by these models, which have a negative chi-effective. Now let's let's compare this to a case where we cut off the data. So in the frequency domain, that means we remove frequencies below 40 hertz. In the time domain, it means we remove times before about 4/10 of a second before merger. So we just cut this data off, and then we analyze again. And you can see here's that 36 hertz power. Now the models are reconstructing something that's over and away from it. So they're no longer reconstructing it because they don't see it. It makes sense. But it's also important that they then shift substantially, implying that this is in some sense like it doesn't look like, or rather the rest of the data wants to make it look like something different, but this power is making it look a different way, if that makes sense. Okay. And so an important thing to note is that this is at the transition region from in-spiral into merger ring-down. So merger ring-down is a more complicated phase, and it also is the parameters interact in different ways to govern the waveform during merger ring-down than they do in in-spiral. And so there's been work by Simona Miller in particular that implies that this transition region from in-spiral to merger ring-down is very powerful in determining how the parameter estimation results will go. Okay, and so when we do this restriction, when we take away the data that may or may not have this power, we see that it shifts the astrophysical interpretation very dramatically. So we shifted from, again, this is something that's almost certainly dynamically formed to something which is, frankly, pretty boring. So this data right here, like 5 hertz in about a 100th of a second, is the difference between a very astrophysically interesting result and a kind of boring astrophysical result. Which is creepy. Okay, data that we know is affected by a glitch is extremely important to the determination of this astrophysical question, is a coupling that you don't want to think about. Okay, but so you may ask the question firstly, is it possible that just the Gaussian noise processes that were happening at these frequencies, if these frequencies are very important to the measurement, then maybe just removing the Gaussian noise process has dramatically changed how the progression of the analysis goes, and it is possible. So we did a bunch of injections, so this means we simulated Gaussian noise with parameters, configurations like this, and then we subtracted them, we didn't subtract them, we computed both restricted frequency and full frequency band, and we compared how the parameter estimation changed, and we found that actually this is a thing that can happen. It doesn't happen super often, but it can happen that you would see this sort of shift in the parameters due to removing this data, even in the case where there is no glitch. So it doesn't necessarily, so the fact that we see this shift doesn't necessarily mean that that the shift is caused by the presence of a glitch in the data we removed, but it is still unlikely for it not to be, if that makes sense. It's not guaranteed that it's due to a glitch, but it has some like p equals 0.9 indication that it would be. Okay. So now let's talk about what we can do about this. So what I was showing you were all results done with subtraction. So subtraction in LIGO data means that this glitch was acknowledged, it was modeled by a glitch inference pipeline called Bayeswave, and what happened was this inferred the properties of the glitch. It took one possible way the glitch was one possible realization of the glitch parameters. It subtracted off that realization of the glitch and presents data that you say, okay, I have removed what I think is the glitch. Hopefully this is Gaussian. Okay, how well do you trust that happened? Is a potential question. So the more robust way to handle this is to instead infer the properties of the glitch and the properties of the CDC at the same time. So rather than relying on a single statistical realization of the glitch, you marginalize over the possible realizations of the glitch. This still requires you to have a good glitch model, but it allows you to much more accurately capture the statistics of what you're looking at. Okay, so in this, I'm going to talk about scattering model. This is the scattering model I was talking about. This is the wavelet reconstruction, so this is what Bayeswave sees when it sees this data, and you can see in particular that it varies pretty wildly on whether it thinks this 36 hertz power was a glitch or not. So the 24 hertz scattering, you can see the blue they're all sort of wiggling at a low frequency. Around 36 hertz power, though, only the wavelet model really finds this, and the wavelet model has very big uncertainties in the reconstruction. Okay. So when I look at the scattering model, what we find is that there is actually some indication. So the scattering model does find power at 36 hertz. So this orange arc, or the burnt orange arch, gets a measurement of scattering being present, whereas the green doesn't. This is weird. It is weird to have power from 3 bounces and 5 bounces, but not power from 4 bounces. Like, how would this happen in light? Unclear, but there it is. But the scattering, as I said, doesn't look like this. So even if it finds power in this frequency domain, or in the frequency band, it doesn't necessarily mean that it's constructing the glitch in the same way. And so when I do this inference, when we analyze to get the specifically scattering model along with the CDC, we find that, as I said, it doesn't really reconstruct any glitch power in this 36 hertz power region, and it constructs a chi-effective, which is actually a little different. It does change, but not by much. So astrophysical result unchanged, though the inference maybe, it has affected the inference, right? The data has changed and it has changed, but the astrophysical conclusion remains the same. By contrast, when you analyze with wavelets, so wavelets are in base wave are more flexible models, so they don't know anything about how scattering got into the detector, doesn't even know that this is scattering, it just says, I'm looking for blobs. Well, so base wave finds actually two possible ways to reconstruct this. Either it finds no power in this 36 hertz, that's, this is a high Q, so high Q in base wave means many cycles. So it either finds high Q and then low negative chi-effective, which corresponds to the result we've been talking about, or it finds a smaller Q, so that's a short, sort of bursty wavelet, and high chi-effective, and that's when it attributes this. So you see this correlation directly that base wave doesn't know whether this is a glitch or not, and it determines then, and like it splits its time basically between whether this is or is not a glitch, and that results in this inference. And it's worth saying that so basically what the deal here is, you can add up the CBC and the glitch in different ways, but when they add up, they will come down to result in the same, that when you add these two things, basically you change the split between them and the relative strength of each split, but when you add them up, you produce the same overall waveform, which is how then you account for these changes in parameters. Okay, so I reached my conclusion. Did this system, which produced 1909, actually have anti-aligned parameters? I cannot tell you. So the power is, so we've looked at this power, and we found that it is not consistent with being a scattering arc, which is the only form of glitch that we know is there. But we can't say, so if this data is really consists of Gaussian noise, a CBC signal, and a slow scattering arch, then this actually is a negative, an anti-aligned spin system, which therefore was dynamically formed. But we can't rule out the possibility that some other glitch also happened. Okay, and then more interesting, I think, are the lessons we can learn for the future. So, firstly, this study was hard. This took 1.5 years of my life, and it's possible with that amount of effort to learn a lot about a given event, but it is infeasible to do this for every gravitational wave event that we see, especially as we see steadily more of them. So we need better ways to integrate glitches into population inference, into our overall machinery of understanding the gravitational wave event, if we want to produce unbiased astrophysical conclusions going forward. Okay, that's the end of my main talk. I have 20 minutes left, so I can talk about other stuff too if people want, or if people are tired and want me to go away. Ask questions if people have any.
Do you want to talk?
Sure, yeah. This is the stuff I talked about at APS actually. So part of this that we looked into is what would be really great is if you had a way to look at a parameter estimation analysis and understand and say this analysis was impacted by a glitch without having to actually analyze the glitch itself. This is possible, interestingly enough. So search pipelines have a lot of statistical tests for whether a result is caused by a glitch. They each have their own, but I'm going to talk about one specifically, the PyCBC chi-square test. I will skip the text description and instead show you basically what we're going to do. This is a weird plot for anyone who has seen gravitational wave plots a lot, but so what we're going to do is we're going to take the frequency domain data, we're going to chunk it up into a number of bins where the integrated area under this curve in the frequency domain is equal for each bin. So that integrated area under the curve is the optimal SNR. So if the integrated area, if the area under this curve is equally distributed, and that means the optimal SNR is equally distributed, then we expect the interaction of this curve with data containing this curve that is basically the matched filter SNR, to also be roughly evenly distributed across those bins up to Gaussian fluctuations. So what this means is we're going to compute these bins such that these are equal, and then we're going to check the matched filter SNR in each bin, and if it's not evenly distributed, then we're going to compute the statistics of how much these matched filter SNRs deviate from the expectation. And if those statistics go outside of chi-square statistics, then we'll say something's up. How am I going to test this? What I'm going to do is I'm going to take a CBC, I'm going to inject a wavelet on top of it that I know will screw it up. So this pink was what I injected as the CBC. I added this orange to it, and now the blue is what the CBC inference is going to produce. You can see it is different. This means that the parameter estimation has been biased because it does not, because the waveform reconstructed is not the correct waveform. And what we're going to look for is I'm going to show you that the parameters are biased and they change as the SNR of this glitch changes. So I'm going to inject this glitch to different SNRs. But as that SNR changes and as the parameters get more biased, we also want the statistic to get higher. And in fact, that will happen. So this is, so this is the mass ratio. So this is, I injected around 0.7. You can see that when the glitch SNR is 0, so when there's just CBC and Gaussian noise, this is reasonably well recovered, and the statistic sits right at 1. But as the SNR of the glitch increases, firstly, the bias increases, and secondly, the statistic increases. So this is actually providing a good test at certainly at higher SNRs of whether the data has been biased by the presence of the glitch. Properly speaking, actually, it's a test of whether the data is well described as the CBC plus Gaussian noise. So for example, this would also pick up on waveform systematics, but close enough. I know this is a CBC plus Gaussian noise because I put it there, and then I also put in a glitch. So I know that it's a glitch in this case. Okay. I'm going to do the same thing with, nope, I put in mass ratio twice. Oopsie. Okay, well, oh well. So the point is, this is a test that works, and now you may ask, what about 191109? 191109 implies that there was something wrong, because this test is actually an abnormal value for the subtracted result. So this is the LBK result basically does produce an abnormally high statistic. Not so high that it's like technically 2 sigma, but it's pretty bad. And then when I do my joint marginalized inference, it corrects it, and it's down to exactly the expectation value. That's cool. Yeah.
For testing this, did you test on the various kinds of glitches that you can see, or
I
just
just did one test.
you just do one?
Yeah.
How confident are you that that one test is representative? And
Depends on your definition of representative. I did intentionally choose a glitch that I knew was super bad.
Okay.
So I knew this glitch would cause an impact. I've not tested this on glitches which potentially could. There are glitches which could be. Which sometimes glitches don't cause an impact if they just don't really interact with the waveform model. Like if the waveform model doesn't have a way to make itself look like the glitch, then it won't try, and the glitch won't matter. I have not tested this on that sort of case. So it's possible that this statistic shows you if a glitch is affecting you, but doesn't necessarily show if the glitch is biasing you. I don't know that. I think it should. I think if this statistic is wrong, you probably do have bias, but I don't have a robust way to say that.
If that signal is not from the glitch, are there any proposed hypotheses how that may be caused astrophysically?
The gravitational wave, like 1909? Yeah, it would be dynamically formed.
Okay.
Yeah, it would be. I think people debated on it, whether it's 2 + 1 or like a second generation and first generation, or second generation, second generation. You know, some people stuck a number on it for likelihood of globular cluster versus AGN. Yeah, people will do their things, but yeah. Yeah, it is almost a prototypical example of what like a smoking gun dynamical formation event would look like. So.
will there ever be a way to categorize that glitch figure out what it was, or no?
Right on.
Okay.
Yeah. I personally think the slow scat, I cannot tell you that there wasn't something other than slow scattering in the detector at that same time. Boy, that would seem super weird though. Like, what are the chances of another glitch also happening at the same time in the same place? Like, really? But, yeah.
But this was both in, it was both in Livingston and Hanford, but because Hanford has,
Hanford, what it was, okay. In Hanford, what it was is it's the same glitch, but it's, if I go back to the start, in Hanford, these tracks were functionally shifted by like pi or pi over 2 with respect to the signal. So it's like the arteries went like this, or like this, and then like this. So it just kind of missed it.
okay.
So it was in the data, but like not affecting the CDC. And we did check if you do or do not provide, if you do or do not cut out frequencies in Hanford, doesn't matter. So
Is it the same physical thing that caused it, or was
it was a different, I think it was a different seismic process. I don't actually know. Sometimes, it could be, I haven't actually checked what the seismic process driving it. Generally speaking, this is caused by microseism, which is waves in the ocean hitting the continental shelf and shaking the continental shelf. So this can get real bad, for example, when there's like bad storms around Greenland that really shake up the waves in the Arctic Ocean. It will make the entire North American continent vibrate, but it'll be out of phase at the two detectors because they're in different places. This could also have been like, it might have been there was one storm in the Gulf of Mexico and another storm up near Vancouver, and yeah.
So, not sure if it's correlated or not necessarily.
Yeah, they're the same process, it's the same physical process, but even if they were correlated motion, the coupling from the motion into the detector is going to be, all kinds of different. So,
Any more questions? If not, let's thank our speaker.